This lesson will cover how to convert between the vector form and the Cartesian form of a line in 3 dimensions. So we're going to start with the vector form of an equation in 3D. So this is r equals a plus lambda b, and if we split a and b into components, we get r equals a1, a2, a3 plus lambda b1, b2, b3. Because the position vector r here represents any point on the Cartesian grid, in 3 dimensions, r is x, y, z. We can therefore write the equation as x, y, z equals a1, a2, a3 plus lambda b1, b2, b3. In a similar way that we did with the 2-dimensional case, we can separate this into its components. So the x component will be x equals a1 plus lambda b1. This rearranges to give us lambda equals x minus a1 over b1. In the same way, we can do this with the y component, rearranging this to give us lambda, and with the z component, rearranging again to give lambda. Now, because they all have lambda as the subject, we can now put each of these 3 fractions equal to each other. So the Cartesian form of the line can be written as x minus a1 over b1 equals y minus a2 over b2 equals z minus a3 over b3. So there are a couple of things to notice here. First of all, we can see that each of the fractions start with x or y or z. We can see that we've then got the position vector of a point on the line. So we've got minus a1, minus a2, minus a3 as part of the numerator. We also notice that the denominator forms the components of the position vector, b1, b2 and b3. So if a Cartesian equation is written in this form, we can fairly easily convert into vector form by simply reading off the values of a1, a2 and a3, remembering to change the sign, and reading off the values of b1, b2, b3 and putting those in there. We will look at the specific case where if the direction vector has a component of 0 for either b1, b2 or b3, there's a slight variation, but in general this will always work. So to summarise the 2-dimensional version, the vector equation is given here, and this can be rearranged into a Cartesian equation, and in 3D the vector equation is here and the general Cartesian equation is here. For each of these Cartesian equations of a line, write down the vector equation. So the first one is 2-dimensional, so we know that the vector equation is going to be in the form r equals a plus lambda b. B is the direction vector of the line, and because we know that the direction is given by the gradient is 5, so we could say that the direction vector is 1, 5. For every 1 you go in the x direction, you go 5 in the y direction. For the particular point A, we could use any point on the line, and the easiest to spot here is the y-intercept, which is 0, minus 3. We could alternatively rearrange the equation into this form and then use the general form from the previous slide. But if we use the values of a and b that we've just found, we would also get the same answer, r equals 0, minus 3 plus lambda 1, 5. So for number 2, there are 2 ways you could solve this to find the vector equation. The first way would be to write each of the components as lambda. So the first one, lambda equals x minus 2. So rearranging that gives us x equals 2 plus lambda. For the second one, lambda equals y plus 4 over 2. So rearranging gives us y equals 4 plus 2 lambda. And for z, we get lambda equals z minus 1 over minus 4. So therefore z is equal to 1 minus 4 lambda. We could write these one above the other. X equals 2 plus lambda y equals 4 plus 2 lambda, z equals 1 minus 4 lambda, and we can see from here that the position vector A, 2, 4 minus 1 is given, and the direction vector, if we factorise out a multiple of lambda, we would get lambda times 1, 2, minus 4. So an alternative way to find the same solution would be to first of all write the x minus 2 as a fraction over 1, and we could then read off the values that we needed. So we know that the values on the numerator with the sign switched gives us the value of a. So we have 2 minus 4, 1 gives us this vector here. And then the denominator gives us the direction vector 1, 2, minus 4. So this is here. So either method will give you the same answer. So for number 3, there are again 2 methods you could use. The first method is to first of all divide all of the terms by 15. The reason we've chosen 15 is because we have 3x, 5y and 1z, and we need something that can be divided by 3 and 5. So 15 is the common denominator here. We can then cancel down those fractions to give us x plus 2/3 over 5, y minus 3/5 over 3, and then z minus 0 over 15. So once this is written in this form, we could then read the values off that we wanted. We can see that a will be negative 2/3, positive 3/5, 0, and b will be 5, 3, 15. So that is the solution there. An alternative way would be, again, to set each of these 3 equal to lambda, rearrange to get z, then use the similar method to above to arrive at the same solution. With question 4, we see that the Cartesian equation is written slightly differently. We have the first 2 components equal, but the third component, z equals 2, is written separately. What we can deduce from this is that the direction vector will be 0 in the z direction. In other words, z is always 2 in this line. It doesn't move in the z direction, so there will be a 0 component there. We can write each of these fractions. We can write the first one as x minus 4 over 1. The second, we're going to multiply by minus 1 over minus 1, so that we have y minus 5 instead of 5 minus y as the numerator. The third one, we're just going to rearrange as z minus 2 equals 0. So from this, we can deduce that the value of a will be 4, 5, then because z is always 2, we can put 2 as the z component of the position vector. The direction vector, we can read the values 1, minus 1, and then because we know that z is always 2, we know that the direction vector must be 0 in the z direction. An alternative way again would be to set each of the components equal to lambda and then rearrange using this form here. We're now going to find the Cartesian equation of the line with the vector equation given here. So we're going to start by writing r in component form, so x, y, z equals 2, minus 3, 1. This time the parameter is t, 1, 0, 5. So from this we can see that x is 2 plus 1t, y is just minus 3, and z is 1 plus 5t. So for the 2 that involve t, we're going to rearrange them to get t equals x minus 2 and t equals z minus 1 over 5. We're going to put the 2 that have t as subject equal to each other. So x minus 2 equals z minus 1 over 5. And then because the y component doesn't have t, we're just going to put a comma, y equals negative 3. What this tells us is that as t varies, the y component will always be minus 3 because the direction vector is 0 in that direction, so the line is not moving in the y direction. Now complete the following questions on exercise 9b, page 204. Questions 1, B and C, questions 3 and 4, and questions 6, 7 and 8.